lot of time to do the job, it would take a lot of time to convert a voltage to a waveform, but it would give you lots and lots of bits because it's very simple to build a DAC with lots of bits. In oscilloscopes these days, especially just across the board, we always think in terms of what's called a flash ADC. That's kind of the technology that oscilloscope uses. And it's a very brute force architecture. It's basically got a number of comparators, 256 for an 8-bit, or 65,000 for a 16-bit AD converter, and you have a bunch of logic to combine them together and just a bunch of threshold detectors to figure out which bits are going to be 1 and which ones are going to be 0. Nice thing about these things is they run really, really fast. This clock cycle, you can convert a voltage value, but they're extremely hard to build, and they have a lot of other, there's a lot of black magic that goes into making those things work. When people think about scopes, they think about that ADC. That's the only kind you can possibly have, because that's a real 12-bit or whatever ADC. In the audio world, they never really used this kind of an ADC. In audio, like in your well, CD players are obsolete now, but I mean, when they came out, you would use something called a sigma delta ADC, which really is a 1-bit ADC. But what it would have would be what they call a sigma delta modulator, which is really just is it above or below a threshold? It's like a 1-bit ADC. And they would sample this at a very, very fast rate. They would oversample. For audio, you need maybe 20 kilohertz of bandwidth. They would sample at a megahertz range, so really oversample. And then they would do a digital filter and a decimator. Inside this modulator, they would do something fancy as well. They would do something called noise shaping, which we're only going to say they do it, and I'm not going to discuss the details of how it works. But by filtering and decimating, what they essentially do is they take the quantization noise and they remove it, essentially, from the resulting waveform. So you basically start with 1 bit, you filter out all the quantization noise, and you get end up with 24 bits of resolution. It's a valid way to do it. It's out there in the industry. It's done every day in audio stuff. So it really is an A to D converter. In the oscilloscope world, we took that step and we thought we'd try to apply that to the instrument and make it a little more flexible. So let's think about it in a little bit more detail. Can you imagine a to D converter that can sample at any rate? It's just a perfect A to D converter. It only has quantization noise. It can sample as fast as you want to sample it. If we run that A to D converter at a specific sample rate, let's say F sub S over 2, and it's an 8-bit A to D, let's say, the quantization noise, if it's ideal, is going to sit there like some kind of a flat noise floor in the spectrum. And the total integrated noise across that spectrum is equal to essentially the resolution, the LSB. So if we take that same A to D converter, running at this speed F sub S over 2, at half rate in this case, and we sample it at a higher rate, then that same noise floor, same noise power integrated, is now distributed over a broader range of frequencies. So I started, let's say, in this case, that my bandwidth might have been a gigahertz, and I run this at a much faster rate, and I limit the bandwidth to 100 megahertz. So I sample this at a faster rate. And then, with this noise floor distributed evenly across the spectrum, if I filter out part of it, I essentially remove the excess noise, the excess quantization noise. And that's the fundamental idea behind a delta sigma A to D. Essentially spread the noise over a broader frequency range and then just filter it. And what happens is, theoretically anyway, all that extra noise goes away. And you get more bits because the quantization noise drops. The integrated noise drops because I'm using a narrower bandwidth. So in our HD mode, what we do is just that. Our A to D converter runs at 10 gigasamples per second in the RTO, 5 gigasamples per second in the RTE. If we reduce the bandwidth using a digital filter and then lower the sample rate, we basically take the existing quantization noise, which is spread over the whole 1 gigahertz bandwidth or whatever scope you have, to that 3, 5 megahertz range or whatever you set it to. And so you essentially gain more bits. And approximately it's 1 bit for every quartering of the sample rate. And that's where we get the 16 bits from. Okay, that's real, right? I mean, that's an AD. Anybody disagree with me? I know what's going to say to me, but you know. Right.
So can anybody else do the same thing that we're doing? Why can't they take it?
I'll cover that. It's a really good point. That's actually a great point. Can anybody else do it? Yeah, it's just math. So here's the other part of it. I said this is an ideal ADC. Well, a real ADC doesn't do this. Okay? A real ADC has spurs and all kinds of other non-Gaussian noise associated. So you don't actually ever get full bit performance anyway. Even from a 12-bit ADC, a 10-bit ADC, or 8-bit, it doesn't matter what the bit count is, you're not going to get all those bits, right? We always talk about effective bits, then the customer's eyes glaze over and we have to talk about it. But it's an important aspect of it. So if you look at that, this is my step here. If you look at that, for example, a comparison of two different RTOs, two different oscilloscopes, this is, I think, the Agilent scope, right? The S series. So we look at, for example, spurious free dynamic range in a scope that purports to be greater than 8 bits. You can see the SFDR down to low frequencies is what, about 57 dB here, and we're about the same right here. This is an 8-bit scope. This is one that claims to be more than 8 bits. What happened is the spurs contain more noise energy or error energy than the quantization noise, so you never get on the inside. This is the reality that we know, we understand that customers don't even care. When they're buying a scope, they look at the bits in the front of the panel, and they don't really get into this stuff. But for you to understand why that is. And at some points, by the way, their SFDR is better than ours, in some places it's worse, like here it's quite good. Interesting to note, by the way, this is a side thing, the SFDR always tends to decrease as you go up in frequency. It's lower because what happens is there's a harmonic that goes out of band on the scope and disappears. But then once you go to a higher frequency of the signal, then you have more underspur. So they always tend to look this way. It's kind of weird, jaggedy shape. So what makes us unique? I think that was the question. That's right. So why are we unique is basically in the implementation. So we do this in our ASIC, so we're doing it in real time. So when we turn on HD mode, it's still streaming through that ASIC in real time. So I get one sample in, one sample out. It doesn't slow the scope down. My digital triggering still works, all my math still works, I get 1 million waveforms per second, all that stuff still happens because it's all built into hardware. Our ADC happens to have really low spurious, which helps this work better on our scope than almost anybody else's scope, simply because most of our quantization noise is actually kind of high noise, less spurs to worry about. So we actually end up getting better gain in this mode. And it looks better typically than a 12-bit, real 12-bit scope. And as I think Rich mentioned before, the HD mode includes the trigger, so you can trigger on the enhanced signal. So I actually get the benefit of the high resolution and high definition on my trigger circuit, which is something that I think is probably the most powerful aspect of it. Now, if you think about LaCroix, and this is something I don't think anybody in this room knows but me, because I talked to Marty Miller about it. The ERES function in the LaCroix scope is an HD mode. It's identical to what we do. It's a filter with downsampling. The problem is it's a math function after acquisition, so you got to acquire the whole waveform, you got to filter it, and then you can display it, and its update rate is even slower than 100 waveforms per second because you have to do this all post-acquisition. It has no effect on the trigger because the trigger is strictly analog anyway. It's a separate circuit of the LaCroix scope. And LaCroix has a pretty big spurious problem. And actually, it turns out their spurs are a little bit funny in the sense that their spurs are way down at low frequencies because of the technology they use to calibrate the scope. It actually ends up shoving all the spurs down at low frequencies. So you tend to see what looks like a phase noise almost going on low frequency. So it's not as effective on their scope, especially at low frequencies. So those are the reasons that it's really unique for us. We do it in hardware, and our ADC happens to be more linear than anybody else's, so it tends to work better. So just to summarize, the HD mode is an application of an existing technology, something that's been around for a long time. We're not creating anything special. There's no black magic involved. It's based on a sigma delta technology, and a lot of times I'll say that in front of customers. They say, oh yeah, okay, I get that, because they remember that. We get up to 16 bits of vertical resolution. We can actually demonstrate that at DC. You can actually see the waveform resolution. And unlike ERES mode filtering, we actually have this ASIC doing it, which allows full operation at full update rate, and the trigger season. And again, the trigger is probably the biggest point. I think.
Awesome. So how many people can go into a customer and explain what